Testing, testing. All right, hello, this is Java, and we're in chapter 7, and we're going to look at figure 713 on page 264 and 265. Now, this program demonstrates the difference between passing an entire array by reference and passing a primitive data type array element to a method. So passing an array by reference. By reference means that we are passing a memory address of where the array resides within primary memory. We're passing a reference, and that reference is a memory address location where the array resides. So if I point to the array, I'm pointing at that array where the first element begins within a contiguous array of memory. The elements of that array are stored within primary memory. I'm not passing a copy of the array itself. That is, element sub 0, element sub 1, element sub, could be 2,000, could be 20,000. And that would be a waste of memory. So we want to make use of passing by array reference. Now, that's not to say that we are unable to pass a primitive data type element as a copy to a method to be manipulated as a local variable value within that method. But the copy can be modified within the method, but there is no change or reference back to the original array in the calling environment. So the original array in the calling environment, its element value would not be changed. So kind of a lot of things to think about with managing passing by reference and perhaps passing, and careful here, it says passing a primitive data type array element. So we could pass a double, we could pass a int, such. So we're looking at our code. This is figure 7.13. It is shared with you. So this is a student data file, so you can test it. Passing arrays and individual array elements to methods. This is our public class pass array. In main, the first thing we're doing is initializing an array. So we're creating a new array. In this case, the array elements are known at runtime, actually within our code. So we are naming and assigning the elements of this array at this point. So we have an array. I just write down it's an int array. We have a reference to wherever this array resides in primary memory, and element sub 0, sub 1, sub 2, sub 3, and sub 4. And sub 0, sub 1, sub 2, sub 3, and sub 4. And at the time that we are declaring a new array as an integer array, we do know its elements, so we're using the list method to list and assign element sub 0, element sub 1, element sub 2, element sub 3, and element sub 4 those integer values. And then we're going to be passing this array by reference to a modifying method. But first we're going to print the values of the original array. And so we're going to output the original array elements. And notice that we have our enhanced for int value and your array reference. We're going to print out the value. So this is our enhanced for statement. And you can read about that particularly on page 262 through 263. But some things that we want to remember about the enhanced for. The enhanced for statement iterates through the referenced array. It's going to start at the first element, the next, the next, the next, the next, until it reaches the end. Each array knows its own length, so we don't have to pass any length parameter. And as it's iterating through the array with value sub 0, sub 1, sub 2, sub 3, it's going to be printing out the value at that subscript, which is 1, 2, 3, 4, 5 in this example. Now, an enhanced for can be used only to obtain array elements. So this enhanced for statement allows us to iterate through the array, and in this case, we're printing the element value found at sub 0, sub 1, sub 2, sub 3, sub 4. So we're iterating through the array, and we're only trying to obtain the array values, the array elements themselves. So the enhanced for cannot be used to modify or change the exact element values of the array. And the enhanced for can be used in place of the counter control for loop whenever code looping through the array does not require access to the counter indicating the index. Now notice here that we aren't printing out the index value. We're not manipulating the index value itself. We're just iterating through the array itself. So the enhanced for iterates through the array from start to through its total length. So the enhanced for is good for examples like printing the elements of the array, maybe totaling the integers of an array, where we're looking at the values stored within each index. And in these two examples, the index is irrelevant, so we could use the enhanced for. Any other time, you're going to have to use your for statement with your starting value and your ending value and your increment value. But the enhanced for is useful in those situations, and the enhanced for statement simplifies the code by iterating through an array, making the code more readable and eliminating several of possible errors, such as improperly specifying the control variable's starting value. Sometimes we forget that there is that 0 element, so we might accidentally start at 1, subscript 1, and those types of programming errors are critical. Or the loop continuation test. Maybe we iterated by 2s and we should have been iterating by 3s. And the increment expression itself. So there's lots of possible errors that can take place within the counter controlled for statement and its conditions. And if we are intending to access the value of each indexed value within the array, then you can use the for enhanced statement. So we're printing out the elements of the array. And so we're going to print out 1, 2, 3, 4, 5. Now we're calling the modify array method, and we're passing array. Now, the name of the array is a reference. So array is a reference to this array that we're passing from the calling environment. And the name of the integer array is array. So this is a reference. So we're passing a reference to the starting point in primary memory, that location. It's a memory reference to where the array object exists. And we're going to print out the values of the modified array are when we're done with processing of the modified array method. So this is a calling statement to our method modify array, and we're passing an array reference. So let's look at public static void modify array, and it's receiving an integer array 2, and we're just calling it array 2 as a different name. But array 2 is a reference. Array 2 is a reference to an array, and it was passed the array reference. So array 2 as a reference is pointing to our array in calling environment. So processing modify array method for int counter equals 0. Counter is less than array.length, and the array knows its own length, so the reference is known for its length. So a reference to array, it already knows its length. We don't have to pass that as a parameter. And we're going to let the counter increment on each iteration by 1. So array 2 as a reference is pointing to counter's value, which is 0 at this time. So the array referenced by array 2 sub 0 times 2. So we are referencing array in the calling environment, and we're going to multiply its current element by 2. So its value now is 2. We iterate, counter is now 1. It is less than the referenced array sub 2's length. The array referenced by array 2 sub 1, its value is 2. Take its value and multiply it times 2. So we are reassigning array in the calling environment to its new modified value 4. Within the modify array method, counter is now 2. The array pointed to by array sub 2 is array in our calling environment. We're looking for sub 2. Sub 2's value is 3, and we're going to take that value and multiply it by 2. So we have modified the array value in sub 2 in the calling environment to 6. Counter is now 3. The array pointed to by array sub 2, the array referenced by array sub 2 is our array in calling environment. counter is now 3. So we're looking at the array referenced by array sub 2, which is array in our calling environment. Sub 3 is equal to the current value 4 times 2, which is 8. Counter iterates to 4. The array pointed to by array sub 2 sub 4. Take that value and multiply it times 2. So it's now 10. And now you can see that passing an array by reference points to the original array in the calling environment. And as we modify, however we modify, we happen to have a simple expression, multiply each element by 2. However you modify each element in the calling environment's array can be and will be changed. We're pointing to one array making modifications by reference to our calling environment array. We're done with the modify array method. So we return to the calling environment. And we're going to print a formatted string. The values of the modified array are, and then we're going to use an enhanced for again to iterate through the array. And we're going to print each value. So we're going to print 2, 4, 6, 8, 10. Now we're going to look at the possibility and the effects of passing an array element value to a method. Now here we're passing an array element value. We're not looking at passing the entire array. We're not looking at passing the array by reference. We're looking at passing the array by element, so by its subscripted value. We're looking at array sub 3, that is a element value within our array before modify element is called. And then we'll call the modified element. So when we print array sub 3, we'll be printing its value of 8. Now we're calling modify element, and this is to be a good reminder. The title in the method itself is reminding us that we're attempting to modify a particular array element. So we're going to call the modify element method, and we're going to pass the value stored at array sub 3. So the value stored at array sub 3 is 8. So we're passing 8 to the modify element array method. Modify element, it is receiving a primitive integer, and we are passing 8. So element is now equal to 8. It has a copy of the primitive value passed by value to the modify element method. So element is reassigned. Element is equal to its current value 8 times 2, which assigns element to element is now equal to 16. System.out print formatted the value of the element in the modified element method as a local variable. We're going to print that integer value in a new line. Element is now equal to 16, so 16 will print. Now that's passing an array element as a copy to a method. And at that point, the value is assigned to a local variable. In this case, element is the name of our local variable. Now we remember that at the end of a method, the local variables are destroyed or returned for active use, no longer accessible. So at the end of modify element, the local element variable is no longer accessible. And we return to the calling environment where we called modify element, and we're going to continue with the line immediately following the calling of the modify element method. We're going to system.out.print formatted array sub 3 after modify element. Now this is after we modified element 3 in a local process. Locally, we had passed a copy of a value from the calling environments array to the method as a local variable assignment. At the end of the method, the local variables are returned for memory use, destroyed, no longer accessible. We want to see what happened to our calling environment array sub 3 after the modify element was called. We're going to print out array sub 3. Well, this is the reference to array. And we want the value at sub 3, which is 8. Unaltered, unmodified. The calling environment array was not modified because we simply sent or passed a value, which was a primitive value, to the method as a copy of the element within the array. It was modified as a local variable assignment within the method. Local variables are returned for memory use, unaccessible following the end of the method. That's our method. Next statement is our trailing method. We're at the end of main and the end of class. So let's see what happens when we run this program. I'm going to open this because I've already tested it. Guess I have to open NetBeans. Too many programming languages this semester. Okay, I'm going to open File, Project, and on my list I'm looking for Figure 7-13. Example 713. Open that project. In my Explorer, I'm going to find my passArray.java file, which is the file on page 264 and 265, and open that in my editor. Passing arrays as reference and individual array elements as a copy to method calls. Public class pass array, our main method, we are initializing our array with known assignments to the elements: array sub 0, array sub 1, array sub 2, array sub 3, and array sub 4. We have 5 elements, 0 through 4 for our indexes. System.out.print formatted. The effects of passing an array reference to an entire array. The values of the original array are, we're using our enhanced for to print out the values of array. The only array that we know of is the array in the calling environment. This is a reference to array, so we're pointing to the array object in the calling environment. It prints out the value at each subscript within the array. Now we're calling modify array, and we're passing array. This is a reference. It's a name reference to it, storing. The name of an array stores the reference to that memory location. So modify array, right here, is the method. Public static void modify array. And we're passing the reference to an integer array sub 2 array. So the reference now is stored in array 2. So as I work with array 2, it's pointing to the array in the calling environment. So for counter equals 1, counter is less than array sub 2 dot length. The array knows its length. So a reference to an array knows the length of that referenced array, and counter is going to increment by 1. Array sub 2. So the referenced array pointed to by array sub 2 index 0, use that value and multiply it by 2. Well, array sub 0 is housing the element value 1. 1 times 2 would be 2. We are referencing the array pointed to by array 2, so that will change the value in the calling environment array. We iterate through the length of the array, multiplying each element by 2, which reassigns the elements in array, the array reference passed to the modify array method. So we've processed the modify array method. Now we're going to system.out.print formatted. The values of the modified array are. We're going to use our enhanced for again to iterate through our array. Array name is a reference to the array. And in the calling environment, each element has now been changed or modified to 2 times itself. So now my array is pointing to the assigned values 2, 4, 6, 8, 10. So we're going to see printed out the modified array values as we iterate with the enhanced for through the loop. We'll see the current assignments to array. Effects of passing an array element. We pass array elements, primary data types, as copies. So we're going to call modify element, and we're going to pass a copy of array sub 3. Zero, 1, 2, 3. So this is now 8. We're going to pass a copy of array sub 3's element value, which is 8, to modify element. So we're calling modify element as a method. We're passing the integer primary primitive data type 8. So element will be assigned 8 as a local variable. Element's current value times 2. Well, we passed a value of 8. 8 times 2 is 16. So we're going to print formatted the value of element in the modified element method is, and element's value is currently 16. We go back to the calling environment, to the statement immediately following the modify element call. And here we're going to system.out that print formatted. We're going to just double check array 3. We want to know what array 3's value is in the calling environment. So after we've called modified element, what happens to array sub 3? An array sub 3 is a reference to index 3's value, and we hope it has not been modified in the calling environment. We passed a copy as a local variable. It was modified within the modify element, but we know local variables are destroyed or no longer accessible when we leave the method. So we want our array sub 3 to still be intact and not modified. So we're looking for a value of 8 to print. So let's run the program. Effects of passing reference to entire array. The values of the original array in the calling environment are 1, 2, 3, 4, 5 assigned with the list method on program startup. The values of the modified array. We called modify array passing an array reference to the calling environment array, and we actually passed the reference to the array, so any reference is to that memory location, the object array. So multiplying each element by 2, we actually are reassigning values within the calling environment's array. Effects of passing array element value. Well, here we passed a primitive data type, the value stored at array sub 3, which is 4, and then we modified that element. Let's see, array sub 3 is 0, 1, 2, 3 is 4. We modified it so it's now 8 2 times right there. Array sub 3, this is array sub 0, array sub 1, array sub 2, and array sub 3. So its current value in the calling environment is 8. We're going to pass that by value to modify element. Modify element receives a copy of the value, which is 8. We modify it within modify element as a local variable. We happen to multiply it by 2. 8 times 2 is 16. And then we inspect back in the calling environment array sub 3 after we did modify a copy. Well, array sub 3 is still array sub 0, array sub 1, array sub 2, and array sub 3. The original array in the calling environment is still intact. We did not modify array sub 3. We passed a copy of that primitive value to modify element as a method. And then we know that within a method, local variables are returned for memory use at the end of a method. And this is a local variable element, so it's returned for memory use, no longer accessible within the program. Well, then we want to look at our program for the chapter 7, your assignment prog 7. And this is on page 300, exercise 7.17. Write an application to simulate the rolling of 2 dice. The application should use an object of class random once to roll the first die and again to roll the second die. The sum of the 2 values should be then calculated. Each die can show an integer value from 1 to 6. Our face values on a dice are 1 through 6. So the sum of the values will vary from, if I roll 2 dice and I look at their face values and add them together, the minimum value would be a face value of 1, and on the second die a face value of 1, so the sum would be 2. And the largest value would be 12 when the face value of both dice are equal to 12, with 7 being the most frequent sum and 2 and 12 the least frequent. Figure 7.28 shows the 36 possible combinations of rolling 2 dice and getting their sum. Your application should roll the dice 36 million times, use a one-dimensional array to tally the number of times each possible sum appears. And then I think in your lesson plan unit assignment, I asked you to print out the sum for this roll, the number of times that sum was rolled out of 36 million trials, and the percentage. So let's see what our program can do for us here. The program simulates rolling 2 6-sided dice 36 million times. We're going to import our java.util random, so we're guaranteed that we get a random generation of the simulation of rolling our die. Simulate rolling the dice, public static void main. Here's our random.random numbers equals a new random number. We have an integer face value for the first die roll and an integer face value for the second die roll, and we're declaring an integer array named totals, and it's equal to a new integer array with 13 elements, 13 compartments. Now 13 would give us 0 through 12 as subscripts. 0 through 12 as subscripts. And we're thinking about rolling the dice. We have 2. The minimum value would be 2. If I first die rolled to 1 and the second die rolled to 1, 1 plus 1 is 2. So we're going to skip element 0 and skip index 1. Logically, it makes more sense for us to say the rolled sums of 2 die equals 2. The rolled sum of 2 die equals 3. The rolled sum of 2 die equals 4. So that's why we're going to skip those 2 declared index values, those 2 compartments. And then, of course, the maximum rolled sum of 2 die would be 12. So we're going to be manipulating 2 through 12 in our integer array totals to keep track of the count for the number of times that the sum of 2 was rolled, the sum of 3 was rolled, the sum of 4 was rolled, the sum of 12 was rolled. So that's how we're logically going to use our integer array totals. Now remember that totals is the name of our array, and it is a reference to the location in primary memory where this array begins to be contiguously stored in RAM. Now we want to initialize our array, so we're going through the initialization process and assign each total subindex equal to 0. Now we're going to simulate rolling the dice. For int roll equals 1, while roll is less than 36 million, we're going to increment roll by 1. And during each roll, we're going to toss the die for face 1, and the dice is rolled, and we're going to assign a value to face 1, our variable, a value between 1 and 5, or 1 and 6. And phase 2 is the randomly generated dice value simulating rolling the second dice for a value for phase 2 between 1 and 6. So totals sub, this is our array, totals sub phase 1 plus phase 2, and we're going to increment that. So totals phase 1 and phase 2. Totals sub phase 1 plus phase 2. This is an index value, and we have an expression here. The current value of phase 1 plus phase 2. Well, let's say that phase 1 was 1, and phase 2's randomly generated toss value is 1. Well, that would be totals sub 2, the minimum value that I could roll as a sum between 2 dice. And then we're going to increment that. Well, that's what we want to do. We want to keep track of the number of times that the sum of 2 die were rolled. So we want to keep track of the number of times that the sum of 2 was rolled with our 2 dice. So we're going to assign total sub 2 to 0 plus 1, so it's now 1. Now the next time that I roll a sum of 2, it will increment by 1. And the next time out of 36 million times that I roll a sum of 2, it will increment to 3, and so on. So I'm done with this roll. I'm going to generate roll sub 2, incrementing roll by 1. This is the second time through my 36 million loop. And this time I'm going to generate a face value for 1 and a face value for 2. Well, if face value is 4 on the first die and 2 on the second die, we're looking at totals sub 6, and I want to increment that. I've rolled a sum of 6, so I'm going to increment. It was 0, initialized to 0, it's now 1. So you can begin to see that as you iterate through the loop, we're keeping track of the number of times that the index value was the sum of the 2 die. So the purpose of your array is to keep a running count of the number of times that the sum is equal to 2, 3, 4, 5, through 12. So when we're done rolling and simulating the sum of 2 die 36 million times, we want to print that table. System.out.printf, and we have a formatted string. We're going to print title, sum, frequency, and percentage. Remember that we are ignoring subscripts 011 for logical reasons with respect to this program design. For integer k equals 2 then, our first subscript, while k is less than totals.length, and of course totals as an array knows its own length, we're going to let k increment by 1. So from 2 to 12, its own length, we're going to declare percent as a double, and that's equal to total sub 2 divided by 36,000. I want to make sure that you've got 36 million, I think is what we did. Might be a typo error. Now we want to divide by the total number of times that we rolled the die. We're going to print out, and I just want to point out to you this format string. I'm going to print out 3 variable values. So in the printed format string, I'm using %3. I want within a field of 3 an integer printed. So that'll be k's value. Percent within a field of 12, I want another integer value printed, and that's total sub k. Our k is an integer incrementing from index 2 through 12. Percent in a field of 12, I want a double output with 2 places following the decimal point as a float, percent, new line. So let's see what happens when we run the program. Closing start and file, I can open my project. And my project is exercise 7-17. Open project. And checking for my file, I have roll-die.java. I'm going to open that in the editor. And we did have an error, simulate rolling the dice. $36 million times. So then in our percentage, when we're calculating percentage, we want the number of times that this sum was counted divided by 36 million. Save all, and let's run the program. It's running, and it's simulating running those tosses and adding the randomly generated face values together and storing in our count array by the name of reference by totals. It did take a little while to do that. Okay, our sum, when the 2 face values were equal to 2, we had a frequency of, let's see, 1,131 times, and that percentage is 27,802. That doesn't look quite right. Nope. Oh, okay. Remember, to get percent, you have to multiply by 2. So by 2, we can take away those 2 placeholders. So percent, we want to move the decimal point 2 places, so let's see if that does it. Okay, this time we have 998,235 times that the sum of 2 was rolled out of 36 million attempts. And if we divide by 36, we get 0.03. Okay, well, I think I'm going to need your help to figure that out for me. So this formula to determine your percentage, and that was an add-on situation. You determine how to calculate the percentage for me and print it out in a nice, neat, formatted way. So we are dividing an integer by an integer, by the way, and then calculate the percentage, the number of percentage times that the count out of 36 million times. So that takes care of this program with a challenge to you. So chapter 7 is done. Unit 7 is available. And now your recording lecture is complete.